Um, with where we left off last class was towards the end of the bipolar junction transistors. Whoops. Whoops. Okay, so this is where we stopped last class. Okay, well, we barely started. So the bipolar junction transistor has different configurations. In this case, which is the most common usage of the BJT, is the common emitter configuration. The emitter terminal is connected, as you can see, common to both the other two circuits, okay, on the left and the right. So the control is marked as the base current. So the signal goes into the base current, as shown here. Okay, so the ES shown here is the voltage input, which can be a switch, right, 0 and 1. And there's a load which drives the current. So when you apply different voltage, the current changes. As the base current changes, we know now that the output, which is the collector current on the top right, will modulate. Okay, so that's the switch. Now, we went through this issue. What happens when this voltage is negative? When the ES is negative, the base emitter junction, which should be forward biased, so you can have hole injection, will become, let's see, when it's negative, it becomes forward biased, so yes, it turns on. Okay? When the ES becomes positive, the base emitter junction, which is here, will become reverse biased, and you will not get hole injection, and the switch is turned off. Collector current turns off, basically. Okay? And for this to work, the assumption is that the collector base junction is always reverse biased. Okay? So those are the two things you really should keep in mind. The two junctions, one is forward biased, one is reverse biased. Okay, if both are reverse biased, it's off. If the base emitter junction is forward biased, it's on. Okay, they're the two regimes of operation. Now let's look at this a bit more detail. So if you plot this would be called the output characteristics, current voltage characteristics of this BJT. The output is the collector current shown here. The input is the collector emitter voltage, and the bias or the control is the base current, which determine these different curves, which is exactly the same as we had for the MOSFET. For the MOSFET, remember we had the drain to source current, drains to source voltage here, and the control was the gate voltage. So it's analogous, exactly the same way. Okay. Now, the key things to keep in mind are that we have what's called the load line, which we saw early on, which is of course determined by the load. You apply the output, okay, which is out here. This is the output. Okay, so you have 5 kiloohms and 40 volt bias. Okay, that determines this load line essentially. Okay, so if the base current is very low, and you get the base current to be very low by applying a positive voltage in this case, you get that point C, where this curve is so small because this junction is reverse biased. This junction is reverse biased, so we essentially have a circuit where you have two reverse biased junctions. Right? You have something like that. Two diodes, essentially, so the current should be 0, right? I'm talking about, okay, just write the terminals here. This will be the collector, and this will be the emitter. Okay, basically 0, right? Two reverse bias junctions. That's this point C. Okay, this point C. Now, when you have this forward biased, this is still reverse biased. This is forward biased means that you can get hole injection. There's another way to think about it, and then you will get a current. Okay, and that's the base current which pushes these curves up. and you get saturation. Okay, this is saturation. So in this case, the emitter base and the collector base junctions are forward biased, and the switch is on. And okay, so if you look at this simple, highly simplified circuit that I drew here, this is the base, right? When this is forward biased, and this is going barely to be forward biased, is when you get saturation. Okay? Because when both the junctions are forward biased, then your input, this output current will become independent of this voltage. And the reason for that is when forward biased junctions, you'll get very low drop. Most of the current is essentially determined by this divided by the resistor. Okay. This is a little bit simplified model, so you don't need to think too much into it. But essentially, when you have these two junctions forward biased, you will get saturation, and the switch can be turned off to be on. The collector base junction doesn't need to be perfectly forward biased, it might be just barely forward biased. Because remember what I said, that the collector base should always be reverse biased for normal operation. Okay, we'll come back to that in a second. The other point C is when the cutoff happens, when both junctions are reverse biased, which is what I drew before, and then the switch is off. Okay, so then anything in between will stay on this load line. Okay, and that is your amplification, right? So you can jump from this point to that point to that point to that point, based on what your base current is. Okay? Now, so what is this load line? I answered this question, but you should be able to calculate it, first of all. Can you tell me how to calculate the load line? Collector current versus collector emitter voltage. Okay. Of course, the simple way to look at it is to look at the two extreme points, right? And then draw a line between. Let's think about the extreme points. The first point, this point C is straightforward because it's cut off. Okay, both junctions are reverse biased. No current is flowing. So that point should be equal to the battery voltage, right? No current is flowing, so there's no drop. Right? Okay. Is that obvious to everyone? It should be relatively simple. It should be like freshman circuits. Right? Look at this circuit. If these two junctions are reverse biased, there's no current. Right? So what is the voltage across these terminals? It's essentially what's in the battery. Right? There's no current. There's no drop across the load. Okay? So that's your point C. Now how do you get the point S? Of course, let me, before I go on, let me clarify that. When these two junctions are reverse biased, the current is not necessarily zero. If you want to be accurate, it is the ISAT, right? Okay, I forgot what it's called, but this small current, right? Reverse saturation current, yes. Right? If a PN junction is reverse biased, you get that current pretty much with respect to the voltage. So if you want to be very accurate, you can put that as the current in here, minus the voltage, and you get that. But it'll be a very small drop, so you could probably ignore that. Okay, now let's talk about how do you get the other. One point's not enough to draw the line, so you need to find the other point. How do you do the other point? I told you the other point is when both the junctions are forward biased. When the junctions are forward biased, what happens? Current flows. What is the voltage drop across each junction?
Very small.
Yes. Yeah, so you can ignore that, again, approximately. So you can basically think about this as a switch which is on, no voltage drop, so you can calculate the current, right? It's just V over R. Okay? So you get that point. It's approximate, it's not exact, but you get that point. Okay? And then you just draw a straight line in between. It's a straight line. Why? Because it is a linear circuit. Okay. Now, if you want to be more accurate, like I said, for the reverse bias, you have to take the reverse saturation current into account. For the forward bias, you know, right? You know this equation, right? So if you want to be very accurate, you can first plug in the voltage. Okay. I see some blank faces. I want to make sure you're able to do this. Okay. This is very fundamental. If you have voltage, you have resistor, and you have PN junction, you should be able to tell me what the voltage and current relationship is. Okay? In other words, if I give you what the voltage is, you should be able to tell, and the resistor is, you should be able to tell me what the current is. That's very fundamental. Okay? Make sure you're able to do this. If you're not able to do this, make sure you ask your friends who are able to do it. If not, then come talk to me. Okay? Okay. So let's see what's. Yes. So we can summarize the operating regimes of a BJT in a very simple diagram. And this is basically the take-home that you want to take away from Chapter 7. Okay, and of course you need to understand quantitatively, but this is basically the picture. Okay, so you have a circuit, and that's a very common circuit, so you can keep that picture in mind as well. You can think about the operating regimes as four quadrants. Okay, and they are based on the base emitter voltage. So you have two PN junctions, right? So like I said, it's based on whether each PN junction is forward biased or reverse biased. There are four combinations, right? One forward biased, both forward biased, the other forward biased, and so on, right? So four combinations, and that's where the four quadrants come from. And it's easy to see here. So you have base emitter junction, base collector voltage. Okay? So, wait a second, that should be, oh no, yeah, base collector. So it is this junction and this junction. So the positive in this case means forward bias, although that can change depending on the polarity of the material, but just look at that for now. Okay, when both junctions are forward biased, like I said, you can think about that as saturation. Right? Essentially, both junctions are forward biased, you get the maximum current flowing through, and the current is pretty much independent of the applied voltage. The reason, of course, we know from before is that when this circuit is forward biased, the voltage drop across the junction is very small. Right? So the current is essentially determined by this resistor, nothing to do with the diode. That's why saturation happens. That's why you need to understand the circuit really well. And then everything else becomes very straightforward. Okay, so that's we know that. Now, I told you that the normal operation of the BJT is when the base collector junction is reverse biased, right? Remember, you have a reverse bias junction whose current is now controlled by the hole injection. That's the principle of the BJT for amplification, right? So the base collector must be reverse biased for normal operation. We know that. So it should be over here. Okay? This should be reverse biased, and this should be forward biased. This is where you get hole injection. Right? Base to emitter hole injection happens. Base to collector junction is reverse biased. Okay? That's amplification. Okay? This is the normal stuff that we've been talking about so far. Of course, if both of them are reverse biased, which is the situation we just talked about previously, no current flows, and the switch is just off. And it's called cutoff. Okay? That's simple. Okay, you can have a small reverse saturation current, but it's pretty much off. Now you can also have an inverted situation, and that's interesting, but it's pretty much the same as the normal active if you think about it. You're switching the emitter and the collector. That's basically it. Okay? It's in the symmetric situation. So if the whole thing is symmetric, if I switch the collector and the emitter, in other words, if I make the base emitter junction reverse biased, and I make the base collector junction forward biased, then I can have hole injection from the collector to the base to the emitter. It's just an inverted situation. You don't need to worry too much about it, but it's exact for our purposes, is exactly the same as active operation. So all you really need to remember for the regimes of the BJT is just three situations here. Okay? Okay, so that basically wraps up chapter 7, what I need you to understand. So just to summarize very quickly, you should be able to know this, what this means. Okay? And that, how to explain essentially this slide, qualitatively and quantitatively. Yes?
I remember from electronics class, but now it doesn't make what sense.
Mm-hmm.
What if you put the signal in the collector?
Yes. So, yes, okay, let's think about, no, the collector is usually the output. Right? You don't have much, well, it's a nomenclature, right? So, okay. That's what I just said. The collector and the emitter can be switched. Okay? So, what I'm trying to say is that if you put the input into the collector, then that collector is actually an emitter, if you want normal operation. In other words, you can switch this whole thing, right? If you rotate this by rotate it by 180 degrees. That's what basically what you're saying. And then it becomes a common base configuration, okay, which we saw before. Let's think about that for a second. So you have base, you have, let's call it collector, base, emitter. Okay? You can have a situation which that's a common base configuration. Now, if you start putting in signal into the collector, in other words, you put a small signal in here, you can, and then your output will be here, right? But remember what we talked about in that situation, the amplification factor is less than 1. So yes, you do it for some special situations, and you don't care about amplification. Sometimes it's useful when you have to do very, I don't know exactly, but I think it has to do with when you need exquisite signal fidelity and so on, because you can get very clear signals, low parasitics and things like that. Okay, but let's not worry too much about that part for the purpose of this class. Okay, I want you to understand the device physics. That's mainly the goal for this class. Okay? Yeah?
I remember maybe the first year we were talking about this, you said that the base is smaller, so holes can get such a lot. But we always draw these, they've always looked the same to me.
Yes, the schematic is not quite right. But remember, the base has to be physically a lot smaller than the emitter and the collector. We'll see that soon. Because the holes must diffuse across. They shouldn't recombine too much. If you lose them by recombination, then your amplification factor goes down. Okay. Physically, it has to be tight, small. Okay? Okay, so I think that was my first slide. So let's go back here. Which brings me to the last chapter, chapter 9. Okay? Which, of course, I'm not going to test you for the final, but I think as for completeness, this is something you should know. Okay? We will, of course, this is a very complicated topic, but we won't really. But I want you to get a broad picture of how these things are implemented. Okay? Chapter 9 talks about integrated circuits. So the idea of how to fabricate these and why are these important, essentially, what has enabled this integration revolution, in a sense, right? Now, and this is the reason why we have been studying all these devices for so long, and why is the CMOS more important than the BJT, things like that. Okay. Okay, so that's basically. Oops. So I started this class with this video, if you remember, the very first lecture. So I want you to look at this again. Okay, we'll kind of pause and go through the different steps, because that's the overview of what happens in the fabrication of integrated circuits. Okay, So let me just point out the key points that make this economically viable, which is basically, at the end of the day, all of this is driven by economics. The fact that one can get functionality at a rapidly decreasing cost. Okay, that's basically it at the end of the day. And the reason for this is the fact that it turns out to be a batch process. Okay, very large number of transistors are essentially manufactured in parallel. Although the manufacturing process is very, very expensive, if you make billions of products, you divide that expensive cost by billions, your total cost per unit goes down dramatically. That's essentially what has happened. Okay? And this leads to lower cost, and also it turns out it also leads to very high reliability because you're making the same thing over and over and over again. Eventually you get very mature processes. Okay, so every device you make, 99.99% of them will work, which means that again you don't lose any money. The other important point is for scaling is that when you make devices small, so in electronics, of course, one would expect that, if you have a junction like this, if you have a big particle that sits on here, schematically drawing, that can short out, right? If you have a conductive particle between these two, then this is no longer a p-n junction. You get shorting between them, and that will not work anymore. So if you have defects, particles, dust particles, whatever, while you fabricate these, it's a big challenge. But of course, if you have smaller devices, the probability of this sort of thing happening is much lower. Okay? So that means smaller devices give you higher yield. So people make more money out of smaller devices, which is why, another reason why people try to make smaller devices, or did try to make smaller. Of course, the main reason that everyone will tell you for smaller devices is that you can put more functionality into the same area, and the fact that your phone has more computing power than your personal computer about 3 years ago is the reason why we buy phones, buy newer computers and so on. So anyway, with those things in mind, let's take a quick look at the video we saw before. Okay, so essentially this is from Intel. It talks about sand to silicon. So of course, all integrated circuits start with silicon, and silicon comes from silicon dioxide, which is sand. Very ubiquitous, very cheap, easy. It's melted down. We talked about this. Okay, it's purified. When you melt it, you can get remove impurities. You essentially form these big cylinders. Okay, it's called an ingot, I-N-G-O-T. You get these big things. And essentially, this gets sliced up with diamond sauce into very thin silicon wafers. And I have one of these, which I will pass around at the end of this video. Okay. And you spin coat what's called photoresist, which is a photosensitive material on top of the wafer. And then you put it in what's called a scanner, okay, which makes these patterns, which is what you will see on this. Okay, I'll pass this around in a second. Okay, once you make the patterns, those patterns define, of course, these transistors, whatever, right? Whatever you put down, it kind of looks like this. Okay, and then you do some processing, which could be implantation, which could be growth, deposition, and then you create all these metal lines, which look like gold. Okay, and then the dies are essentially chopped up. So that's the principle. And you get these tiny dies. They're all repeated, as you will see on this wafer. Okay? And the robot comes in, picks up a die, and it gets packaged. And that's kind of what you will see on this. And gets packaged onto a chip. And the whole field of packaging, of course, is also very complicated, and we won't really talk much about it. And that's what happens. Okay? The patterns. The functionality, of course, obviously comes from the patterns that you put down in that photoresist layer, and then that gets repeated several times to create multiple layers and so on. Okay? So that's what you have studied so far in terms of BJTs and MOSFETs and so on, of course, translate into some physical device, right? Which we'll see, which you have seen before and we'll see again. So I'll pass this around. Essentially, these are I'm not entirely sure what kind of devices these are, but they're representative electronic devices. So this is about a 3-inch silicon wafer. This is what it looks like you have seen before. And essentially, you will see a whole bunch of repeated patterns. And I believe they are just metallized circuits. So basically, you probably have silicon, polysilicon, and some metal. It's my guess. I haven't actually looked at it. It's brittle, so try not to bend it. It'll break, okay? They're crystalline. Okay, so, whoops. So another way to think about this whole thing of trying to make things smaller and smaller together is, and this is kind of pertinent because I was actually at Boise last week at Micron, which is, I guess, close by company which makes memory devices. And one of the big things that they work on nowadays is the fact that memory turns out to be the limiting factor in your computation. So how fast you do your computing, watch your video, whatever, online, has to do with the fact that the CPU trying to communicate with the memory becomes a bottleneck, okay? And one way to address this bottleneck is to bring the memory closer to the CPU, okay? So if you think about it, if you have, okay, the example is actually here. So if you look at this, okay, so you have a CPU and you have some bus which connects, basically a bus is just a channel of communication which connects to some memory, okay, some memory bank. The one development that happened was that this communication channel turned out to be the bottleneck. And that was probably about, I would say, 10 years ago, okay? And of course, to reduce that bottleneck, what people did, they took this memory and put it on the chip itself. So you physically made them closer together. So the electron velocity is fixed, right? So the speed of transmission would be distance divided by velocity, right? So it's the time taken for transmission. So to reduce the time, you reduce the distance, okay? And this is another reason why scaling is important. Smaller devices can be put closer together, okay? And that's what they call the L2 cache, which is outside the CPU, L1 cache, which is built into the chip. And nowadays, of course, people are trying to do something much more crazier, which let me see if I can get it. This is actually from Micron, and I thought this was interesting because I learned about it last week, but it's been going on for a while. They call this a hybrid memory. Okay, so the idea is to make a three-dimensional memory device. And let me see if the video kind of shows it. Okay, anyway. So the idea is that the memory so far has been a two-dimensional plane, and of course that limits it, so they want to stack lots of them in 3 dimensions and put them very close to the CPU. Let me see. All of this is not so important. Okay, so this is, by the way, what a fab looks like, if we haven't seen, and we'll see this again. Okay, there's a wafer going in. The whole thing is clean. You have to wear a bunny suit, typically. But paradoxically, in the most advanced fabs, actually, you don't wear a bunny suit. Because, okay, so let me talk about this. This is what they call the hybrid memory cube. And we'll see what a memory is. But okay, what they did was essentially they took a portion of the CPU functionality, put it as a logic at the bottom there, and then built the memory right on top of it. And they made a 3-dimensional device, essentially. Okay, so it's a collaboration with Samsung and Micron, and they stacked many wafers together. Fairly complicated process, but they think they'll make money, okay, because this is the big bottleneck. Okay, and they're marketing it for very high-end servers like this and so on and so forth. I don't remember if there's any more technical detail. Probably not. I don't think there is. Okay. Now maybe let's see. Oh, okay, so they talk a little bit about it. So the idea is that you can get much faster performance. So first of all, you get more memory within the same volume, and because they're closer together, you have faster access. And also, you put some of the logic of addressing the memory from the CPU onto the memory itself, which means that you can relieve the CPU to do more important things. So overall, from a system architecture perspective, the whole thing becomes very, very fast. So this is something which has not a product yet, but they have announced it, and this is something I think they will They're trying to make into a product. So the idea is that. So you can see there's a CPU, right next to it they want to put this hybrid memory, and the idea is that there can be a lot of this hybrid memory. Okay? As you will see, because it can is optimized for power, things like that, as shown in that schematic. Okay? One other important development that's happening, okay, I think that's just clear. Let me go back here. Is that, and you probably have heard of it, is that there is this move to multiple cores. So instead of one CPU, you have multiple CPUs. Okay, and then I think I know this laptop probably has 4 CPUs in it, and most of your laptops probably do. Most of the advanced ones have 8 or 12 and so on. And this has to do with the fact that, has to do with 2 things. Okay, one has to do with the fact that when you scale, the chips start running hotter. And this has to do with the off current that we saw last 2 classes ago. Okay, the subthreshold slope. You have some current flowing when the transistor is off, which means that you are generating heat even when you're not using the device or when the device is on standby, which means that as you pack more and more of these together into a very small area, you're producing lots of heat. Something like what I was told actually last week was that they produce about 100 watts in a tiny, tiny chip. That's a lot of power coming out. Okay, you can cook on it. So this is something you have to deal with fairly carefully because, of course, if you get really hot, you can destroy the device. It'll slow things down. Remember, when things get hot, the mobility of the electron goes down, if you remember. Okay? It's like T raised to minus 3 over 2 or something like that. Yeah?
I went to Iron Flash yesterday.
Yes.
There was a question, but I forgot. What are the wafers made round? What do the edges in the wafers has? Will it be?
Yes. It has to do with the ingot. You saw the cylinder? Okay, there are 2 reasons. First of all, it is grown as a cylinder. Okay, it's not grown as a square. Second of all, if you make it a square, you end up with stress, which will break it. So these are very specific crystalline direction that it's cut on. So if you make it, you will see it. If you try to cut a silicon wafer into a square, it will not be very stable. It'll break very, very easily. That's the primary reason. It's easier to handle. By the way, this wafer I'm passing around is only 3-inch. In manufacturing today, and you probably saw it at Diamond Flash, it's about 12-inch. It's that big, about that big. It's pretty incredible if you think about it. It's that thin, or maybe a little bit thicker than that, but that big. So, of course, the reason to make that larger is that you can get more chips in the same wafer. Right? So it's obvious. It's the same idea of batch processing. Okay. So, and I saw another interesting statistic, which I didn't put here, but that the entire electronics industry is something like 1/3 of the entire world economy, something like that. It was ridiculously large, which is, I suppose it is believable, but I saw some large number like that. Okay, so there are different types of integrated circuits, so you should be aware of different things. There are different ways to classify them. You can think about them as linear circuits, which are essentially all the analog circuits that we saw. Okay, not switches, but the amplifiers. So whenever we said the BJT acts as an amplifier or the MOSFET acts as an amplifier, those are called linear circuits. Okay, and they kind of look like this. Those are the op-amps you saw in your circuits class, amplifiers, analog communication circuits, things that you use in your cell phones, things like that, routers, okay? As opposed to digital circuits, which are CPUs, right? This is what we're familiar with, what goes in your phones, computers, all that stuff, not for communication. Okay, digital means it's a switch, 1s and 0s. So again, switch versus amplifier. Remember the amplifiers when both these junctions are, well, this junction is reverse bias, this junction is forward bias. Switch is when both of them are the same. All forward bias, all reverse bias. Okay? So try to relate that back to your device physics. Another way to think about ICs, integrated circuits, is that they can be monolithic ICs where the entire device is on one chip. So that's what the CPU looks like. Or you can have hybrid ICs where the multiple ICs are combined with discrete devices. So you can look in this example, you see there is probably an op-amp here, there's a CPU here, there's probably a memory here, whatever. And they're all connected. And there might be capacitors and resistors, which are discrete elements, not integrated. So you can have hybrid system. And I would say the vast majority of chips are probably hybrid. Okay, the cheap kind of chips. Okay? Of course, integrated circuits are also called chips. Okay, so scaling. So scaling, of course, we have seen it a few times, refers to the historical evolution of the size of the devices over time. Okay, so they've gotten smaller, and you've heard of what's called the Moore's law. Okay, the idea of Moore's law essentially is shown here, where and we saw this in the beginning. The horizontal axis is the year, and the vertical axis is the transistor count. We started in the 1970s with about 2,300 transistors per chip. This is per device. And today, 2011 or so, we are about 2.6 times 10 raised to 9, 2.6 billion. It's more than that now, because it's a couple of years old. Okay? And that evolution, of course, it's only 40 years, right? 40 years, you've increased by 6 orders of magnitude. Okay, and this is a logarithmic plot, and you get pretty much a straight line, and that's what's called Moore's law. Gordon Moore, who founded Intel I think it was in the 70s, predicted that the number of transistors will double every 18 months or so. Okay, and that prediction pretty much came true because of a variety of reasons. Some of it, I think, is just self-fulfilling prophecy. Okay, meaning that there was economic requirement that this has to be met. And they did everything they could to actually meet it. So, it kind of self-fulfills itself. But obviously, it had to do with technological improvement as well, and clearly. Okay, so that's a pretty remarkable curve. 6 orders of magnitude improvement in about 40 years. I don't think there's been any technology in the history of the human race that has undergone this kind of evolution. Okay, so that's why it's kind of important. And we are kind of out here somewhere where we are facing lots and lots of challenges. So that's why this is an interesting area, because you're reaching kind of an interesting limit and new ideas are required. Okay, so that's why I think this class hopefully has introduced you to what has been done before, and you can think about what, if you do go out and work in this industry, you'll get a sense for what sort of things that need to be done in the future. Okay. Scaling, of course, can also be looked. The reason for that increase in the number of transistors per chip has to do with the fact that each chip is smaller, and that's summarized here, where, again, from Intel, you can see. In 1999, they had this is, of course, a MOSFET. You should be familiar with this now. You have a source, you have a drain, and you have a gate oxide and some gate, right? Okay, the gate length, which is the distance between the source and the drain, is scaled as you get smaller and smaller and smaller. It was about 180 nanometers at 1999. That is the distance from here to here, approximately. And it went down to 130, 90, 65, 45, 32. And nowadays, it's not really top secret because they have actually announced that this is a couple of years old. It's about 22. I think more recently they've shown below 10 nanometers or so, 8 or 9 nanometers. So the idea that the field effect transistor that we learned works, and by the way, people did not believe it will work below about 20 nanometers, but they have actually made it, and it works. Okay? Clearly, when you have very short channels, if you go back and think about your field effect transistor, all the short channel effects come into play, particularly the high field. Right? You have the voltage across a very small distance, you get very large field, which means that the mobility will saturate. Okay, so you can have current saturation without having pinch off. Okay, and you have ballistic transport, you can have tunneling, so that's all these issues that people need to deal with, but it still works. Okay. Let's see. I'm going to skip that. You can watch this if you want. I'll post a link to it. It shows you. It's actually an interesting. Sure, I'll very briefly say. They're interviewing several people who were involved in the early development of the ICs, like Gordon Moore, and they talk about what has happened. It's by a fairly well-known scientist, Michio Kaku, who does lots of popular science shows. So you can watch. I'll post it online. I'll skip that. Okay, now let's the rest of the class. Let's think a little bit about some details of the process integration. Okay, we'll focus on CMOS, which is complementary MOSFET, because that's the most. I would say something like 80% of chips made in the world are based on this process. Okay, a small amount is of course BJTs, and another small amount is when BJTs and CMOS are combined, and this is called bi-CMOS. Okay, and we'll start with the most ubiquitous device. Okay. This is perhaps the building block of all digital logic. Has anyone seen this before? Okay, that's good. Okay, essentially you have a NMOS device and a PMOS device connected in series with VDD on top, this at the ground, input voltage at the gates of the two transistors, output voltage at the drains of the two transistors. Okay, this circle means it's PMOS. That's a circuit device. Okay, so I want you to do this exercise yourself. What is V out if V in is 0 volts? So take about a minute, talk to your neighbors, and think about what happens. You have sufficient knowledge to do this, so I expect you to, by the way, to be able to answer these kinds of questions as well. Okay, so the hint, of course, is that the threshold voltage for the NMOS is what? It's positive. The threshold voltage for the PMOS is negative. That's the hint. Those are the hints. Now figure it out. V out is 0. Sorry, V in is 0, so it's grounded. Okay. So, yeah. Look at the what does on mean? Okay, so first of all, it's very simple, right? When you have 0 volts on the gate, so the first question to answer is which transistor is on? It is the NMOS, right? Because the threshold, it is higher than the threshold voltage. 0 volt is enough to pull the electrons to the channel. So the top transistor, sorry, the PMOS, my mistake. The PMOS is on, my mistake. NMOS is off. Okay? Now, if you think about this from a very simple switch perspective, the PMOS is on means this is essentially a closed circuit with low resistance. NMOS being off means this is an open circuit. Right? So what's V out? Yeah. So V out gets pulled to VDD. Okay? This circuit closes. Okay? So of course the next question is what is V out if V in is greater, some positive number. Imagine it's greater than the threshold voltage of the NMOS. Yes. Exactly. So what is the logic? It's a logic device. So what is it? It's a what? Someone said. Yes. It's an inverter. It's a NOT gate. You send in a 1, you get a 0. You send in a 0, you get a 1. So you see, this is nothing but what you've learned before, right? NMOS, CMOS transistor. If I put it in a configuration like this, I got an inverter. With an inverter, I can build any logic circuit. which I assume you must have learned in your digital design class. Okay, that's all I need to know. And I can build anything I want if I have billions of transistors the way I connect them. Okay, now I can do digital logic. Oh, okay. Last question. Spend about a minute. Think about it. What is the current flow from VDD to ground? In either situation. Yes. It is 0. Why? Yes, exactly. That's another beauty of this design, is that it uses very low power. Right? The current from the battery, which is VDD, to the ground is basically 0, irrespective of how you use it. There's a small current that flows when it switches its state. As we know when we talked about switching in MOSFETs, capacitance and switching. Other than that, the current is pretty much 0, which means a low power device, which is why you can use billions of these. Okay, so this is a very beautiful design, very simple, and very important. Okay, of course the logic, the answer is this is an inverter. You send in a V in, you get a V out, which is opposite. It's low power consumption because if you plot the ID, you get it's mostly 0. You get a small current when the switching happens, and you can of course integrate this into billions of devices on an IC. Okay, that's a device that's the only device you really need to know. Okay, how to integrate. Of course, there's one more device we'll talk about, which is memory device, which is a little bit different. This is logic, and memory is different. And of course, analog devices are much more complicated, but digital devices make up about, like I said, about 80% of all devices. So at least you should know that. Okay. So this is what the integrated device looks like. Okay, you've seen this before, but let's just walk through it again. So you have a PMOS side here, NMOS side here. In this particular case, of course, you can have different ways to do it. But in this particular case, you start with a P substrate. Okay. For the NMOS, let's start with the PMOS channels. For the P substrate, let's start with the NMOS. Sorry. For the P substrate, the NMOS it's P, right? So you don't need to do anything special. All you need to do is define the drain and the source with N type. Okay, so you create this PN junction, and that's all you need, and you need the gate shown here. Okay, so you have the drain here, source here, gate here. As you apply gate voltage, the electrons get pulled close to the channel. It completes the circuit from the drain to the source. Okay, that's our NMOSFET. For the PMOS, and of course I said it needs to be on the same substrate. Right? This has billions of these have to be integrated. For the PMOS, of course, we need to make what's called an N-well. N-well means that you need to make a region which is N-type within this P-type wafer. Okay, and after you have that, and we'll talk about that in a second, you can define the source, which is P+, drain, which is P again, and then you have the gate, and again you apply negative voltage, the holes get pulled to the channel, and the current flows. Okay? You have a P-type, N-type, and if you connect this drain and this drain, as shown here, this is a metal, so they're connected together, that's our V out. Okay? This gate is connected to this gate, not shown here, it's out of the plane, that's our V in. The VDD goes to this source, the ground goes to this source. So, yeah, this source. Okay? This is the integrated version of that device. So in order to understand digital integrated circuits, this is the only slide you do need to know. Okay? Of course, there's a couple of things which are important. One is you see this big silicon dioxide region, and that has to, of course, to do with the fact that you need to separate, isolate the NMOS device from the PMOS device. Because if you don't do that, if you look carefully, this N, this P, and this N will form another FET. Right? And we talked about this. This is the parasitic FET, field effect transistor. To avoid that happening, you make this silicon dioxide very thick. In other words, you prevent this metal from acting like a gate. You're increasing the thickness, so no matter what happens here, you don't actually form a channel here. You put it far away, just like here. Okay, we saw this before. Okay, is that clear? Because this is the picture I want you to take home from chapter 9, basically. Okay. Okay, now the details of the fabrication, of course, are complicated. So let's try to go through it one by one. Here there are 14 steps to make. Let me think here. This is just one device. Before we go into it, the beauty of the process is that, like I said, it can be batch process. So the whole thing is automated, goes through machines. Humans never touch it. Okay, this is totally enclosed, so it's completely clean, all that stuff. So there is, although it looks complicated, all of this is fairly straightforward, completely automated. So let's begin. Okay, let me see if I can zoom in. Yeah. Okay, let's begin here. Okay, so a silicon substrate. Okay, you put down what photoresist, and this is the side view. That's the top view. Okay, the blue thing is the photoresist. You put something down, you create a pattern. Sorry, the blue thing is actually the oxide, I think. Let me zoom out again. 1 second. Yes, blue thing is the oxide. Okay. So you put on photoresist, you make, okay, the blue is oxide, then you put photoresist on top. You make a window in it, so you expose to the pattern, which is that flashing thing you saw in the wafer floating around. You saw those lines. Okay. These are just windows that are open in the photoresist. Then you etch. Okay, you remove the oxide, but you preferentially remove the oxide only in these regions where you are trying to form the MOSFET. You leave the oxide in between to isolate the MOSFETs. Okay, so far so good. Then you do what's called implantation, which we saw before, which is basically bombarding the whole thing with either boron or phosphorus to make it N-type or P-type. In this case, I don't know what it is. Let's see. Boron. Green is boron. Okay. Boron means it's group 3, so it's acceptor, so it's making it P-type. Right? Okay. Then you so you get a pattern which looks like that, of boron. Everything else surrounded by oxide. Then you put down photoresist again, everywhere. Then you define, okay, it's everywhere again. Then you define the window in between, which is to define the gate. Okay, these two things are the source and the drain. Okay, you etch through the oxide, you get a window there for the gate. Okay, then you put down a metal. Oxide, silicon dioxide. Let me make sure. Yeah, gate oxide. Hafnium oxide, gate oxides, high refractive index. It doesn't have to be silicon oxide. That's this yellow stuff. So you get oxide here. No, this is not right. There should be no oxide there. I think that's a mistake. I mean, you see that, right? If you just put oxide down, it should only be here, not in the source and the drain. So I think that's just a type of mistake in their figure. Okay. Now you have defined the gate oxide. What happens? Next, you need to put the contacts in. So you define photoresist again. Okay, you open up the source and the gate. Yeah, I think that's still a mistake. I think there's they forgot to put that in. But you open up the source and the gate so you can define the contacts. You put down metal, right? You need to contact the source and again you need to form an ohmic contact. In this case, they put aluminum, typically. I think the purple is aluminum. Let's check. Yes, the purple is aluminum. So that's just a contact, okay? So that's where are we? Oops, we are here, step 10. Okay, so we have defined the aluminum here, and aluminum on top of the photoresist, but then you remove the photoresist, all the aluminum out here is gone. Okay, you end up with something which looks like this, where you have a metal contact to the source, metal contact to the drain. Okay, and this is what it looks like in the top here. The gate oxide is still there, you still need to make a gate electrode. Okay, that's the next step. So you put photoresist again. Just skip the step. You open up the gate oxide. But you can also open the source and the drain because you probably want enough metal to actually contact it out. Okay, so you open up the gate oxide, which kind of looks like that. It's a little bit shifted, so you can actually contact it from the side with metal. Later on, you will see that. Okay, and then you put down aluminum again. So on the source and the drain, you just build up more aluminum. On the gate, you build up aluminum on top of the gate oxide. Okay, and then you remove the photoresist, and you pretty much have your device. Okay, what you have is you have a contact, metal contact to a P-type region in an N-type substrate, gate oxide, gate contact, source or drain contact, P-type. Okay, so you have your device. All you need to do is now contact them with metal. Yeah, it's not shown here. But what happens at the end of the day is that you basically put some metal lines to contact them. Some metal lines run across this way, horizontally. Okay, so that's a process. It's okay if you don't really understand it. I would say go through it carefully yourself. It's not too complicated. Okay. I won't go through the details of this, but this, actually, or very quickly I can go through. It shows the different processes, actually says what they are, so you can actually correlate them, but very, very quickly. What happens is, again, you start with a P-type silicon wafer, you oxidize the silicon, create a field oxide, the isolation oxide, which is the same as what we saw before. Then you etch the oxide after lithography to define the MOSFET region, the source and the drain. So, okay, in this case, we are creating the N well for the PMOS and the NMOS, so this is for CMOS, okay? So the way you do it is you open up a window and you diffuse, in this case, phosphorus, a donor. So you create a local region that's N-type in a P-type substrate, okay? And then after that, it's exactly the same as before. You create so you open up a window here, you have a window there. You grow the gate oxide, you deposit polysilicon to connect to the gate oxide, you etch the polysilicon to create the source and the drain, okay, and that happens on both sides for the P and the N. Then you implant the source and the drain. This side becomes N+, this side becomes P+, so CMOS. And you grow some protection, passivation, just called nitride. You etch the nitride. The nitride is just there to protect the oxide. Don't worry too much about it. Then you put down metal. That's it. You contact them. So this is your inverter, by the way. That is the device that I showed you 2 slides ago. That you see here because they're connected in series. Okay. Then you etch the metal so you can separate the source, gate, the source, gate, drain. These 2 drains are connected together. Okay, this is our inverter circuit, pretty much. This is the output terminal. The input terminal are the gates. This goes to VDD. This goes to ground. Right? That's how you make the inverter. Okay. Just to recap, to make the N well, as I said before, is essentially you define with photoresist a window and you basically bombard with phosphorus. So you can create a region which is locally, in this case, P-type, N-type, sorry, phosphorus. Okay? And that's what's shown here, and then you can grow an oxide on top. For the P well, you do the same opposite. You bombard it with boron. Okay? So it's pretty straightforward. I'll skip that. This is not so important. I'm going to skip that too. Okay, there's an important process innovation that happened, I would say 5, maybe 10 years ago, which is called a self-aligned spacer process. So you saw in all those steps, there were quite a few lithography steps. You had to spin resist, you had to do an exposure, you had to do develop, you had to do etch. You had to do this many times, and that's a problem because every time you do these steps, it costs money, time. Okay? So they try to minimize that. And this was an interesting, simple innovation to minimize that. So the idea is very simple. Okay, so let's say you have an N-type source, N-type drain, and your gate is defined there. What you do here is you grow oxide, okay, silicon dioxide or glass everywhere, it's all over the place, and then you do what's called an anisotropic etch, which means that the etching happens only in one direction, vertically, straight down. Okay, you remove the oxide. Now, if you see what happens is that the oxide over here is thicker vertically than the oxide over here and here. Okay, so at the end of the day, you end up with some silicon dioxide remains. Okay, now you have created these silicon dioxide barriers without actually doing any lithography. Okay, just from a single etch. So you've gotten rid of like 12 steps. Spinning, resist, develop, etch. With like 1 step or 2 steps because you have to grow the oxide. Okay? Now the oxide in this particular case is used to actually diffuse to make this N+. So in this case what they do is they use the oxide as a mask and put boron. No, wait, phosphorus. I'm always thinking. So you implant phosphorus to make this N+. Of course, to make the source and drain N+ means to get a better ohmic contact to the metal. Right? That's the reason to do that. Okay? You still leave a lightly doped source and drain region right under the oxide. The oxide will prevent the phosphorus from going through. Okay? Again, the idea is that there's always, what I want to convey is that there's always a lot of innovation happening in the process and to try to minimize the steps, making it cheaper, faster, more reliable, things. There's a lot of very important work going on there as well. Okay, so one term that you will encounter in this whole field is basically ultra-large scale integration. So there's all kinds of different acronyms or jargons, basically, which define how integrated circuits are classified over time. And this has to do with how many circuits are packed into a small area. Okay, ultra-large scale integration is what we just passed. And what we are now is what people call gigascale integration and so on. So, and there's all these kinds of words. But anyway, so I just picked this as an example so you can see. So this is a 256 megabyte DRAM cell, the memory, which we will talk about next. We haven't talked about memory yet. Okay, for Micron, you can see over time how it has gotten smaller. Okay, this would be considered a ULSI chip. Another good example is the Apple Power PC. This is a 90 nanometer gate length device, and it's a hybrid chip. Okay, let me zoom in. You can see the details here. So you have where's your CPU? Okay, there's a floating point unit where you do the digital calculations, fixed point units, memory subsystem. There's cache memory, which we just talked about. Okay, this is a single chip which included everything, right? Logic, memory, and level 2 cache. So the cache which is closest to the CPU is called the level 1 cache, iCache, Dcache, all this kind of stuff. Anyway, that's what a Power PC from Apple looks like. This is, by the way, the A6 microprocessor, which is Apple's most recent chip, which probably is the most advanced microprocessor out there, I think, commercially available. And this is a 45 nanometer gate length device. Okay? There's all kinds of interesting things. First of all, you have CPUs. Okay? You have GPUs. So you can see there are 2 CPUs here. They're identical, by the way. Do you see that? It's symmetric and identical. And then you have GPUs, graphical processing units. Okay, and there are 3 of them. And 2 of them, sorry. And there's a controller for that. Oh, actually, there's 3 of them attached to a controller. And there are there's the cache memory, and there's what's called the PLLs. Those are analog circuits. So in this case, you have both the digital and analog incorporated together to get a very, very powerful processor. So this is it's pretty complicated. I would say there's probably more than 1 billion transistors on there. Okay, so the last topic that I want you to know is memory. Okay, memory is important because, like I said before, memory is the bottleneck now. It's not the CPU. The CPU is as fast as it. Well, it can go a little bit faster, but it's really not the bottleneck for a computational perspective. Okay, it's the memory. Secondly, the reason it's important is that we have at least 2 or 3 local companies which make memory. Ion Flash being one, Micron being another. Okay, so if you end up working, several of my students ended up working at Micron, so I know it's an important area. And the device physics is a little bit different than logic, so let's try to understand this. Okay, I'm going to skip that video, and we can come back to that if we have time. Okay, There are different kinds of memory devices. Okay, there's static, there's random access memory, first of course. Of course, memory has many different meanings, right? You have a hard disk, okay, which goes in a computer, right? That's not a random access memory, it's a sequential access memory. In other words, you have to go through all the, it's like a book, okay? It's like a book versus you have to actually thumb through every page to get to, say, page 55, as opposed to random access, you can go directly to page 55. That's the difference between conventional memory or hard disk versus random access memory. Random access means you can randomly access whatever page you want, right? So that's the first difference. Within random access memory, which is what we're talking about, we're not talking about the hard disk. Within random access memory, there are three different kinds of random access memory. One is a static random access memory, which we will start with, which basically means that the memory value, whether it's 1 or 0 or whatever, is held while the power is on. Okay, in a dynamic random access memory, the memory value is also held when the power is on, but it needs a refresh. It needs to be refreshed periodically, dynamically. And the last one is flash. Flash memory, which is what IM Flash makes, by the way. And this is the sort of memory which does not require power. This is the sort of memory, by the way, which you put in your camera to take pictures and so on, right? The little stick. That's what IM Flash makes in Utah.
Same as in solid state hard drives.
Yes, solid state hard drives are basically these kinds of devices as well. That's correct. That's why solid state hard drives are different than conventional hard drives, which use magnetic media, which we won't talk about. Okay, so that's the landscape. So now let's try to understand what, from our understanding of transistors, what is a static random access memory. Okay, this is what the simplest, one of the simplest to understand, not necessarily the simplest, SRAM looks like. So the idea is the holds memory value while power is on. So, So let's see what this means first of all. Okay, before we look at the transistors, first of all, we have what's called a word line here. So this is a row column addressing for memory. So you have basically a grid. So you address one row. Okay, you have what I call bit lines. You have what I call word lines. And if you pick this, and let's say you pick that, then you read that thing out. Right? And so that way you can pick out any grid. So that's a basic architecture. So you have a word line coming in. So this is one unit of that architecture. So we're looking at one of these. Okay. And you have a bit line here. Okay, you have a complementary bit line. The line on top means it's inverted here. Okay, this is ground. This is VDD. Now you have 6 transistors here. Okay, these two are NMOS, M1, M3, M5, M6 are NMOS, M4 and M2 are PMOS. Okay, and I want you to think carefully. If the Q is the value that's stored, okay? Q bar is the complementary value. So let's say, for the sake of argument, the value stored is 1. Okay, Q is 1. So Q bar is 0. Okay? If Q is 1, it's connected to this gate. Which transistor is on? Correct. M1 is on. Okay, M2 is a PMOS, so its threshold voltage is negative, so positive voltage means off. Okay, so that's the first thing to remember, is that this transistor is on. Okay, Q bar is 0, so if you look over here, which transistor is on? M4 is on. Okay, we'll keep that picture in mind. So M4 is on means VDD connects down to here. Right? This circuit is closed. Okay. Now, if I query this transistor, if I put a 1 on this bit line and 1 on this word line, what happens to M6? So let's say I put 1 on the word line. What happens to M6? Turns on. Right? Then I can complete, if I just put 1 there, this transistor is on already, because my Q is 1, Q bar is 0. Now I turn this transistor on, which means that I complete this circuit. Do You see that? In other words, the bit line will quickly go up to VDD. Do you see that? Okay, let's do it again. So Q bar is 0, because Q is whatever is stored there. Okay, I'm just saying it's 1 for the sake of argument. Q is 1, Q bar is 0. If Q bar is 0, look at transistor M4 is on. Okay, it's PMOS. It's on. Okay, now I turn on the word line. So M6 is on. So M4 and M6 are on means that this circuit is complete. So now my bit line will very quickly go up to VDD. And I can detect that. But more robustly, you will see if you follow the same logic, this low bit line bar will actually go to ground. And it's easy to see because M5 is on, M1 is on. So this circuit is closed. Okay? So if I take a differential between this bit line and this bit line, I will see a big spike. So I can read a 1. That's how it works. Okay? The analogous logic works for 0 as well. Won't go through it. So the picture is shown here. If Q is 1, if you want to read the memory, you apply word line, you apply logic 1 to word line WL, and you read out the difference between bit lines. Okay? I showed only one here, but typically there's 2 coming up, and we look at the difference between these. So query this, and you apply a high here, you read this out. You see a 1. See, this bit line will get pulled up to VDD, this bit line will pull down to ground. Okay, the opposite will happen for the other situations. Okay. To write is basically the same approach as well. A bit more complicated, but that's the idea. Okay. So think back, just by knowing or treating the transistors as simple switches, that we know that the device is complicated enough, now you can understand how simple digital logic could work. Digital memory could work. Okay. For dynamic random access memory is a little bit different. It's a much simpler configuration. So you will see that DRAM is cheaper than the SRAM, typically. Okay. The idea is much simpler. All you do is you basically have a transistor attached to a capacitor, and the capacitor holds some charge. Whether you have lots of charge there means 1, if you have 0 charge there, it means 0. That's basically it. And all you do when you turn these on is basically you turn on this transistor and you access the charge here. Okay, so you turn this gate on, and this whatever charge here gets connected to this line here, and you query this line. Okay, it's exactly the same as the SRAM, but except now that you will discharge this charge. So when you read it, you lost the memory. So you have to replenish it to give the charge back. And there's complicated circuits to do that. You don't need to understand, but that's the basic idea. Okay. Okay. The flash memory. Okay. This is what IM flash makes here. So you guys should know what it is at least. Okay. It's actually very simple. It's essentially the MOSFET structure. So you have an N source, N drain, and you have some P-type substrate. Okay. And you have 2 gates. That's what's special here. You have what's called a floating gate. So it's an electrode, conducting thing, that's separated from the channel by an oxide, very thin oxide shown here. But you also have a control gate on top. So you have 2 gates sitting next to each other, and they're separated by an insulator. Okay? What happens essentially is that you use this control gate to impart charges by tunneling into the floating gate. And the floating gate essentially almost acts like a capacitor which holds the charge. You charge the floating gate. Okay, which means because it's separated by an insulator, it can hold the charge even if the power is turned off. Okay, so if you have a positive charge here, is the transistor on or off? In the floating gate, let's assume there's some positive charges hanging around. This is P-type. So if you put a positive charge there, what happens? You pull the electrons close together, push the holes away, you invert the channel, you create a channel, you close the circuit, so you will see a current flow through, so it's on. On the other hand, if I put a negative charge there, I will push away the electrons. Okay? I might pull holes, but if I've designed this to be a very short channel device, it's mostly depleted, so there's no holes there anyway, and it'll be off. There are lots of details which go into how to make it, but basically that's the idea. Okay? So you query that and look at the current which flows through. And you can write it by applying a voltage to the control gate. Okay, that basically brings us to the end of the class. So Tuesday we will not have a class, but I am around. If you have questions, feel free to come to my office during the class time or email me. The finals next Friday, 9 o'clock, 1 hour, 2 questions. Chapters 6 and 7. Okay? Here, yes, yeah. In this room, yes, yeah. Fill the survey, okay, when you get a chance. It's important for me anyway. And good luck. Well, I really enjoyed the class, so I hope you took away quite a bit from it. So, thank you. Yes.